So in this lecture, we're going to discuss the notion of hashing. So we're going to start with the concept called the associative arrays. And the idea is that when you think about an array, array is really a mapping between the numbers from 0 to n that are mapped into some set of objects, object 1, object 2, and so on. So you think of an array as a mapping. So array is a very interesting data structure. We can store a lot of different things in the arrays, but the problem is that we have to store them by this key, which is an integer. So when you store something in an array, we have to know where to put it. And once we have it there, then we can apply any type of algorithms to find certain things about these objects. But we are trying to take that idea and try to generalize it to a concept called the associative arrays. The associative arrays are really arrays that can have sort of a string as a key. So if you give me a key like, say, Guna, I'll be able to map into some location in the table. So I'll map into some location in a list using this key called Guna. So in order to find that mapping, since the tables are really stored by an index, we got to take this Guna and map that into some sort of an index between 0 and n minus 1. Once you do that, then you'll be able to find the location for that record in a table where the index, if you compute that the Guna index would be I, and then you would be able to store the key here. So the idea is that you're trying to figure out, using just the key, where to put it. And then that location is kind of unique to the key, because that depends on what the key is going to be. So that kind of leads us to a concept called a hash function. So what we do is we try to find a function which will take a key and then somehow give us a number between 0 to n minus 1. Now you can think of many keys to do such a thing. So for example, many functions to do such a thing. You can say, let's take the function h of a string, where you would add the characters of the string from 0 to, say, n minus 1. So in other words, you take all the ASCII values of the characters and just add them up and get a number. And then you can probably take that number and mod that with the table size m. And here we got a function. So you can do that for every string you have in your key set. So that can be done. So the finding a function is essentially finding something there. You take a string, key string, and map that into some integer in the range from 0 to n minus 1. In this case, I'm going to call this n. Let's assume that the table size is n, so we can map into 0 to n minus 1. All right, so why do we study, why do we care about this? We care about this because we got a bunch of strings that we like to insert them into a table. But when we insert them into a table, we want to insert them into a very special data structure, which is based on a table, where we can do inserts and finds quite well. So in other words, that on the web these days, you got to store a lot of data. But if you put them in random places, it's going to be very difficult to find. So you got to have some methods to store the data so that data can be found very easily. So the idea is not just to insert, the idea is also to find it. Now, we do know that there are many data structures that we can use to store data and find them. Like, for example, if you take an array, to insert an element into an array can be done in big O of 1, because all you have to do is just stick the elements to the end of the array. We know that even if the array is not big enough, we can use some sort of a amortized cost analysis to show that we can do inserts into an array in big O of 1. On average, cost of inserting one element into the array is big O of 1. Now, finding an element from a random array would cost you O of n. You will have to look through the entire array to find this. If you have a sorted array, you can insert something into the array. It would cost you big O of n, since you have to find the location to insert, and then you have to shift the elements to the right to maintain the sorted invariant. But finding something in a sorted array is efficient. We can do that in log n using algorithm like binary search. If you have a linked list, then you can insert something into a linked list by big O of 1. If you really don't care about the order of the insertions, you can always insert the element to the beginning of the list. Finding an element in a linked list, a random linked list, would cost you big O of n. You will have to look through the entire list to find it. The worst case complexity would be big O of n. If you have a sorted linked list, it would cost you big O of n to maintain the sorted invariant. So you can do the big O of n insertions into a sorted linked list. As we saw in one of the homeworks, that there is no advantage to having a sorted linked list and finding something, since we cannot apply a concept like binary search on a sorted linked list, since we do not have any sort of index defined on a linked list. If you have a queue, insert means that n-queuing into a queue. So you can do that in big O of 1. You can stick the element into the back of the queue. But finding something in a queue would cost you big O of n. You will have to dequeue all the elements and look at them and n-queue back and recreate the original one. If you have a stack, the stack, you can push something into a stack in big O of 1. But finding something would require us to really pop all the elements from the stack and somehow adjust the stack later to the original state, but it would cost you big O of n. So if you look at this table, the complexity of insert and find is either when it's big O of 1 for the insert, when it's big O of n for the find. So there's no data structure that can give you both of them in big O of 1. So our concept of the associative array is to figure out how to organize data such that data can be stored and found in big O of 1. That's a very, very interesting property, because if we can do that, that's a very efficient data structure. But it only does inserts and finds. We are not going to worry about the other operations such as finding max or finding min or finding median. That sort of order operations we are not going to worry about. So the idea of hashing, this leads to the idea of hashing. The idea of hashing is that we got a bunch of keys in a set. So these keys are ideally strings, but it can be anything. So the idea is that you take a key and using a hash function, you apply the hash function to the key, and then you find a number between 0 to the table size. So if you have a table of size n, we find a number that will fall into 0 to n minus 1. Once you find that number using a hash function, we'll be able to store the element k3 in that location. So the question is going to be, how do we find such a hash function? Like I said before, we can think of a simple hash function. If you take the string ABC, you can say, well, that's going to be a plus b plus c, where I would assign a equals 0, b equals 1, and c equals 2, which is very simple to compute, and you get the number 2. You could also then compute maybe h of BAC. That also gives you, if you compute that, that also gives you number 2. So although it's a simple function, there's a problem with what we call collisions. In other words, two keys, so two different keys mapping into the same number. So what do you do in a situation like that? So we'll talk about that in a little bit. So we had the concept of, we're talking about hash functions. Hash function is essentially something that takes a key and map that into an integer between 0 and the table size minus 1. So let's talk about some of the desired properties of hash function. As we saw, when we take a simple functions like ABC equals a plus b plus c, in other words, in general, you're going to say, let's take a string, let's add them up, the characters, which is easy to do. You can use the ASCII table values of these characters to do it, and then you can figure out what the number is. So it's easy to calculate, so that kind of satisfy this property, but it doesn't minimize collisions. For example, we can say that all the permutations of ABC are going to give you the same character. On the other hand, because A, B, C are assigned numbers close to each other, like 0, 1, 2, and even close permutations of the characters sometimes can create very similar behaviors. You can get the same value. Even if they're not permutations of each other, it's likely that you can get something pretty close to each other. So you're going to have a lot of collisions. So one possibility is to compute this as some sort of a polynomial computation. So let's call this, let's take some p, some prime p or base p. So we'll take ap squared plus b times p1 plus c times p0. So in general, you can say, well, if you take a string which is given like s0 to sn minus 1, we can define a function which is really sigma s0 p to the I, where the I will go from 0 to, let's call it, either way we can go any way we like here. So I will go from 0 to n minus 1. So when I equals 0, you'll get s naught p to the n minus 1, and then we will have, at the end, we'll have the s of n minus 1. Okay. So choosing a hash function, the ideal way to choose a hash function is even the small changes in the input string should result in unpredictable change in the output hash value. So that's a very important thing about that, because even if the keys are pretty close, K1 is pretty close to K2. Let's say K1 is like ABC, but K2 is like ACC or something, where B and C are pretty close to each other in the ASCII table. But ideally, we would like these two things to produce numbers that are really very unpredictable. So let's say this creates a value like 2,583. This would create 10,781. Ideally, that would be the ideal case of having this sort of a hash function. So we can do that if you can find a proper function to compute the hash codes for all of these strings. Now, one of the hash functions you can use is to generate pseudo-random numbers is this particular hash function, where you take a string and you take a table size, and you make sure that your preconditions and your postconditions are satisfied. You expect the m to be some value strictly greater than 1, and then you expect the result to come between 0 and m minus 1. So the idea would be that we choose two numbers that are relatively prime. Again, we're not going to go into the details about what this method is, some of the mathematics behind this. This is the linear congruential random number generator. Now we can take a seed. In seed, that you can take any hex number as a seed. We find the length of the string, and what we do here is that we go through the length of the string. So we go from S0 to Sn minus 1, and we try to compute the value for the hash code. Now, if you step through this list, what you would find is the following. Let's start with the value of h. H is going to start from 0. Let's say I is going to start from 0. So when h is 0, I is 0, what you're going to get is the character at the 0th location. So let's call that s of 0. So your h is going to be, in the first iteration, because h is 0, you're going to get h equals just s0. And then the r gets changed to something else. So notice that we are changing the seed at every iteration using those two numbers that are relatively prime, a and b. So the next iteration, the I becomes 1. And now if I becomes 1, you're going to compute the next value of h. So h is going to be some sort of because h was s naught before, So you're going to get R times S naught, that's going to be the new H, R times S naught plus the character S1. Okay, so and then S becomes 2, and then you're going to get R squared times S naught plus R times S1 plus character S2, and so on. So what you're really seeing is that we are generating a series of things. We are constantly changing the seed R, so it's not the same base that we are using for all of them. Now we are computing more as a polynomial. So ideally, that all of these numbers, for even if you do some minor changes to the string characters, it should generate a fairly unpredictable number. Now it's possible then we take the mod once you get the sum. So the sum would be sort of like a polynomial addition. And then that we assert that the number has to be between negative m and positive m. If it's negative, we make it positive, and then we return the h. So we always return something positive between 0 and m minus 1. Now in languages like Java, the r is not changing. In other words, here r is changing based on these two prime numbers, a and b. I mean, two relatively prime numbers, a and b. But in Java, the r is taken to be 31. So r is kept as a fixed number. Still, it generates a fairly decent set of random numbers. Okay, so the implementation of the associative arrays can be done using a data structure like this. What we're going to define is an array of linked list. So why do we need linked list? We need linked list because if two keys map into the same location, let's say in this case the location is we have 0, 1, 2. Let's assume that. Let's assume that when we take the h and when we apply k1, when we apply h to k1, we end up with 2. Same thing happens if you use k2 or if you use k3. So k1, k2, k3, no matter how good the random function is, you're still going to map into the same location. Because the only way you can assure that you're not going to map into the same location is to have a very large array where every key is going to be unique. But if you have a finite table size, you're going to have collisions, and then you're going to have to chain it up. So the way you're going to do that is to all the collisions will be chains. Our goal is to keep these chains as small as possible. We don't want very long chains. Like for example, if your hash function is bad, you can have all of the things that are mapping into the same location. So you can have a situation like an array of linked list where you have all of the keys are mapping into the same location. So in that case, the search would take you big O of n, which is kind of bad because that's not what we're looking for. We're looking for something where we can get the search done in big O of 1. So ideally, your hash function must be good so that it can distribute the keys in a random way. So ideally, given any index, so there's an equal chance of any key mapping into that index. Now, we talked about how long what the load factor would be. Load factor is sort of defined as the number of keys in the table divided by the table size. Now, ideally, we like to keep the load factor close to about 2. In other words, on average, we have 2 keys per chain. So when we search for something, we don't do worse than 2 operations. So that's ideal. If the hash table gets too big or the load factor gets too big, that means there are too many hash keys in the table and the performance of the hash table can go down. So therefore we have to go through a process called rehashing. Rehashing is a concept where you take the old table, maybe you double the size of the table, you take all the old keys, compute the new keys, and rehash into the new table. So in terms of average case analysis, as we saw, ideally if you have a table of size m, let's take a table of size m, and then if you have n keys that you like to store in here, so ideally we like to have n over m keys per chain. So if keys are equally distributed, then we can say on average it will take n over m complexity to find a location. So like I said, let's just keep it constant, like something close to 2 per operation to find it. But the worst case is still possible. The worst case would be that it would cost you big O of n to find. So in case all of the keys map into the same location. So we need to make sure that our distribution is fairly random, and therefore we have a good chance of distributing, putting any key into any location without having any biases. So it's very important. So we'll talk about the code in the next lecture.